So today I'll be discussing about freezing point depression. What is freezing point depression? The phenomenon known as freezing point depression illustrates why adding a solute to a solvent causes the solvent's freezing point to drop. So to further explain this, on the left side of your screen you will see ice or water without a solute. At certain temperatures, specifically 0 degrees Celsius or 32 degrees Fahrenheit, the water molecules will stop moving, and they will start lining up and crystallizing, therefore hardening, and water as a liquid state will become ice. On the right side of your screen, we have water with a solute. And if you can see the solute particles here, they actually uh, give the water molecules a hard time to align with each other and to make a solid structure and become ice. So this is a broad explanation on why adding a solute to a solvent causes the solvent's freezing point to drop. Now a good example of this, and an example that we will use to solve a problem later, is salt and ice. So our formula would be Tf, delta Tf, freezing, or the freezing point of the solution is equal to I, the ionization or Van't Hoff factor, multiplied by Kf, or the cryoscopic constant, multiplied by the molality. Now, our sample problem is going to be 31.65 grams of sodium chloride is added to 220 milliliters of water at 34 degrees Celsius. How will this affect the freezing point of the water? Given that the density of the water at 34 degrees Celsius is equal to 0.994 grams per milliliter. Our molar freezing point constant is also given, which is equal to 1.86 degrees Celsius, kilogram per mole. Now, the first thing we need to calculate is the molality of the solute, which is your NaCl. And to calculate this, we need the atomic mass for both sodium and chloride. So that's why we have this. The atomic mass of sodium is equal to 22.99. And the atomic mass of chloride is 35.45. To get the moles of sodium chloride in this situation, we just simply need to input 31.65 grams times 1 mole divided by 22.99 plus 35.45. These values are your atomic masses. And a few quick calculations, you should end up with this answer, 0.542 moles. So next we have kilograms of water is equal to density times volume. Now we already have density, we discussed it earlier. It was given, which is at 34 degrees Celsius, our density is 0.994 grams per milliliter, multiplied by 220 milliliters, multiplied by a constant 1 kilogram over 1000 grams. And a few quick calculations, you should end up with 0.219 kilograms. Now back to our original molality formula, which is moles of NaCl over kilograms of water. Now we already have these values, moles of sodium chloride, which we got earlier, 0.542 moles, and our kilograms of water, which is 0.219 kilograms. We simply need to input these values, and a few calculations, we should end up with molality is equal to 2.477 moles per kilogram. Mole per kilogram, rather. Number 2 is to determine the Van't Hoff factor, which is I. So the Van't Hoff factor is the number of moles of particles formed in solution per mole of solute. Now sodium chloride completely dissociates into the two ions, namely sodium and chloride, Na plus and Cl minus. Therefore, I or the Van Hoff factor, is equal to 2. So the third step is to find the delta TF, which is the freezing point of the solution. So the freezing point of the solution is equal to I, the Van Hoff factor, multiplied by Kf, which is the molar freezing point constant, which we have, and the molality, which we solved earlier. So input these values here, multiply all of them, and you should end up with Tf, or freezing point of the solution, is equal to 9.21 degrees Celsius. So 31.65 grams of NaCl, or sodium chloride, was added to 220 milliliters of water. In conclusion, it will lower the freezing point by 9.21 degrees Celsius. So that's all for our PowerPoint presentation, and that's all for my presentation on my behalf. I hope that I explained this well, and yeah, thank you for listening, teachers.